Then we'll look at section 4.5, derivatives of inverse trig functions. Our objective is to find the derivatives of the 6 inverses of trig functions. We found the derivatives of inverse functions just in general last week. That was g prime at b equals 1 over f prime of g at b. We use that formula. But if we're working with inverse trig functions, there's a little bit more to it, a little bit of an easier way to look at it than that, but also a little bit more to it in terms of our thought process. So let's see what we can do. Let's figure this out. These are just your basic graphs of trig functions, but I want you to remember that last year we learned that you have to limit your domain. If I go through and look at these, none of these trig functions are one-to-one. You had a problem on the homework when we were doing inverses of functions where it was a parabola. It was not one-to-one, so what did we do whenever we were looking to find the inverse of that? We limited the domain. We looked at it and said, okay, we're just going to look from 0 to infinity, x greater than or equal to 0. We want to be able to do the same thing here. So we want to limit our domain. This is the domain that your calculator uses. This is what other people are using whenever they start to find inverses on these. So as I do this, I want every possible value, negative to positive, that I can get for sine. If I choose going from 0 to pi, then I get 2 of my positive values and no negatives. So that's not any good. And since I'm starting at 0, I want something that helps me right in there. So what I will do on these is look at this piece right here. And I will go from negative pi over 2 to positive pi over 2. And that limits my domain to that space. It gives me every possible value from negative 1 to positive 1. So I'm in good shape. Cosine, I want the same concept, every possible value from negative 1 to positive 1, but starting at 0, it works very nicely. Just come down like this. And so my domain on it is from 0 to pi. On tangent, remember your odd functions all work the same and your even functions work the same. So tangent is going to back up and it's going to go from, we'll put our other asymptote over here, it's going to go from negative pi over 2 to positive pi over 2, limiting my domain. Cotangent, although it looks nice and like I could go from 0 to pi, because it is the reciprocal of tangent, we do change that. And I will be looking just at this little piece right here and this little piece right here. So it is the reciprocal of tangent, so I want to use the same domain, negative pi over 2 to positive pi over 2. Cosecant, that's the reciprocal of sine, so I want to back up to negative pi over 2 all the way to positive pi over 2. Negative pi over 2 to positive pi over 2, just like it was with sine. Secant is the reciprocal of cosine, therefore it operates on that same domain again, 0 to pi. Okay, so not too bad, pretty simple. On the next slide, what we're going to look at is the graphs of these inverses. Remember, to find an inverse, you trade your x and your y. So we've traded these x's and y's, and right here is my y, negative 1 to 1. So that means that this right here, since I traded these, this is my negative pi over 2. This right here is my positive pi over 2. On the inverse cosine, it goes from 0 to pi. Inverse tangent, negative pi over 2, positive pi over 2. And if you look at these and you think about your tangent graph that runs right in through like that, you can tell that these are flipped across that line y equals x, which is what our inverses always do. Now then I copied and pasted this graph off the internet, and then I noticed when I was getting ready that this is not the correct graph, okay? Your cotangent graph, because it's going from negative pi over 2 to positive pi over 2, this is the graph of your inverse. The other part that you see in black up above should be ignored. That is not part of your domain. Negative pi over 2 to positive pi over 2 should match up with your inverse tangent. Secant is good, going again from 0 to pi. And cosecant is good, going from negative pi over 2 to positive pi over 2. So those are the graphs of the inverse trig functions. Hopefully we remember that from last year. Okay, I want to look at this real quickly and remind you that if I asked you to take the derivative of y equals x squared, you would write y prime equals 2x or dy dx equals 2x. And what you always thought you were doing was taking the derivative of the right-hand side. I said take the derivative, you said the derivative of x squared is 2x, and on the other side you just wrote dy dx without thinking about it too much. But what's really happening is that you are taking the derivative of both sides. You're taking the derivative of y with respect to x, and you are taking the derivative of x squared with respect to x. When I take the derivative of y with respect to x, there's no x in this right here. There's no x there. So the derivative of y is 1, but then because I'm taking it with respect to x and there's not an x, I have to put either a y prime or, in this example over here, dy dx. Now I will typically write the dy dx, I like this form the best, because I know that I took my derivative with respect to the variable x. That lets me see it much more easily. Over here, I'm looking at 2x, but let me tell you, when you take the derivative of x with respect to x, let me rewrite this real quickly so that we can see. Derivative of x with respect, derivative of y with respect to x, and the derivative of x squared with respect to x. Yes, this one over here we talked about, that goes to 1 times dy dx. This over here goes to 2x, and I took the derivative of x with respect to x. That's what allows that to go away. You're still doing that on both sides. It's just that we so seldom show this because that goes to 1. And that's what leaves us just with the 2x on the right-hand side. So we're actually doing the same thing on both sides. It just doesn't always show up. And it's a fairly detailed concept that we're going to get to here in a few more days. So it's not something we generally introduce at the beginning. Well, let's see how to do this now. Okay. I need that because as I look at this right here, I've got y equals the inverse tan of x. Well, if I want to find dy dx, I cannot take the derivative of inverse tangent at this point. So I'm going to, I'm going to take the tangent of both sides. Tan y equals tan of the inverse tan of x. Well, tangent y, I'll let that sit there for just a moment. On the right-hand side, when I take a tangent of an inverse tangent, that allows those to act as composition of functions. When we did f of x composed g of x, if our functions were inverse, we were always left with x. And that's what we're doing here. We've got these two functions that are composed. They are inverse functions, so that's going to leave us with x. Now then, I want to be able to take the derivative. So I'm going to, on both sides, take my derivative with respect to x. On the left-hand side, I know the derivative of tangent now. I didn't know the derivative of inverse tangent, but I know the derivative of tangent. That is secant squared y. But I was taking the derivative of this with respect to x. Okay, since there's no x, I have to have times dy dx there. Equals derivative of x with respect to x. That is technically 1 dx over dx. But again, this right here is going to go to 1, so we don't really worry about it. So now then, solving this, I have dy dx equals 1 over secant squared y. Well, you know, that's really not a lot of help, because if I'm trying to solve, if I have y equals inverse tan x, and I'm trying to solve this, I don't have a y value. I need an x value. So I want to go back to this equation right here, and I want to use it to draw a graph. Or a sketch, maybe I should say. Last year, when we were doing trig functions, if I saw tan y equals x, that told me that y was my angle, and that x over 1 was the ratio of my sides, because tangent was opposite over adjacent. Well, that means then that my hypotenuse is the square root of 1 plus x squared. Okay, that's simple enough then. If my hypotenuse is 1 plus x squared and my sides are 1 and x, then when I go back down and look at secant, secant is the reciprocal of cosine. Well, cosine is adjacent over hypotenuse, so I need to be doing hypotenuse over adjacent. That means that this right here is 1 over the square root of, my hypotenuse is 1 plus x squared. Over the 1, I do not have to write the 1. So I have 1 over 1 plus x squared. This was secant squared, so therefore this is squared. And I get 1 over 1 plus x squared. That is my derivative. The derivative of the inverse tan of x is 1 over 1 plus x squared. Okay, so we needed that little bit from the last to understand about the dy dx. We needed our picture from last year, this right here, in order to be able to understand where we would get our 1 plus x squared. Now we know that the derivative of the inverse tangent is 1 over 1 plus x squared. I can use my x that was given to me in the original problem, and I am in good shape at this point. Your other inverse trig functions look very similar to this. They all have 1 minus x squared, or x squared minus 1, or 1 plus x squared. They're all in terms of x. Okay? If you will notice, arc sine and arc cosine, remember arc sine, that's the same symbolism as sine to the negative 1x. Calculators generally use the sine to the negative 1, but arc sine is the exact same thing, and it is used quite often as well. They are used interchangeably. So we've got this right here. Your tangent and arc tangent and arc cotangent are the same except for the sine. Your arc secant and arc cosecant. So those co-functions like that always match up with each other. Again, noticing not only do they match up, and if I memorize, 3 of them, as long as I remember my arc sine, my arc tangent, my arc secant, then I've got everything else done, because arc cosine is negative, arc cotangent is negative, and arc cosecant is negative, just like, or the derivative of these are negative, just like they were on my regular trig functions as well. Okay, so derivatives of arc cofunctions are negatives, and they should match up with the derivatives of their cohorts. Okay, so let's differentiate now arc cosine x, let's differentiate y equals inverse cosine of e to the 3x. I put your formula down over here because I don't have to derive this anymore. I know it now, or at least I should know it. These have got to be memorized. So I've got it right there. I'm going to show you how to use that without having to derive it like we did on the earlier one. This has on it, let me get my little highlighter for a moment. This has e to the 3x right here that is in place of that x right there. Okay? Which means that it also needs to go in place of that x right there. Okay? Since I have e to the 3x that I'm taking the inverse cosine of, and taking the derivative as well. That's what's got to go in every time I see an x. So, the derivative of the inverse cosine of e to the 3x equals -1 over square root of 1 minus e to the 3x squared. But I'm not done. Because e to the 3x, I can take the derivative of. So by the chain rule, derivative of e to the 3x is e to the 3x. And then apply the chain rule again. Derivative of 3x is 3. So your final answer on this one is -3 e to the 3x all over the square root of 1 minus e, and remember power to power you multiply, so 3x times 2, and we'll get 6x there. And that's your answer, and you're done. So once you have those formulas memorized, it's really easy to use this. Okay, no problem at all. And there is your assignment. So just get those memorized, and then you won't have any trouble using them. See y'all later. Bye.